Okay, we have now a circuit with two batteries and two resistors. It's still really simple, but we're adding the complexity of another battery here. And what we're asked to find is just the current through each resistor and the current through point A. So basically, we're being asked to find the current through all branches of the circuit. So a branch of a circuit is simply following a wire from one junction to another junction. So I'm going to explain quickly here. If I were looking at a branch on this circuit, here are the branches of this circuit. One branch might be, let's see, here are my two, whoops, sorry, I meant to change that color. I have two junctions or nodes. Sometimes they're called nodes. We tend to call them junctions, but you might have heard them called nodes before. So I have two junctions in this circuit, yeah. And so if I go from one junction to the other, and I can call this like, I don't know, junction A and junction B, if you want, there are three ways for me to get there, right? From one junction to another. One way is to kind of go up and around and then down, right? That's one branch. The second way for me to get from A to B is straight across from A to B. And then the third way is to go down and then back up. So those are, and I'm not trying to like map out currents or anything here. All I'm doing is trying to define for you what a branch is. So a branch is simply a way to get from one junction to another junction. And it can be useful to know how many branches are in a circuit because that's the same as the number of currents in a circuit. Each branch will have a unique current. So in this particular circuit, notice that there are three branches, and we're basically being asked to find the current in each one of those because there's a resistor in the top branch, there's a resistor in the middle branch, and then there's this little point A here that I threw into the bottom branch. Okay. So there are a couple approaches to this problem. The first approach that I'm going to take is having us look at potential, right? Probably not a surprise to you. So I'm going to go ahead and go through and highlight my different potential values. Um, I have green up already, so I'll just start with green. I'm just going to start in a random place. So I'll start just highlighting here. This is some elevation, right? That chunk right there is some elevation. And I'll change colors, highlight this chunk over here, this wire. These are just wires. Remember, when we're labeling elevation, we never go through a component because components change elevation, or we never go through a current carrying component, I should say. I have one more color. So I don't know, I'll use purple. Okay, so I have three elevations in the circuit, not a ton. I have three. So let me go through and see what I can do as far as just labeling these right from the get-go and see how I can do here. I have to make a guess at what the lowest point in my circuit is, and it doesn't matter if I'm right or not. You might remember that we've done a little bit of that. But I would say maybe the bottom of this 9E, this big battery, right? This battery, the 9E battery is obviously bigger than the 6E battery. So I'll say, hey, what if the low side of that? My guess is that the low side of the 9E battery is going to be 0. So that's how I'll label my 0. I know at the 9E battery, I step up 9E. I'm going from the negative to the positive terminal here. So I step up a 9E. That tells me that this red here is going to be up at 9E, right? Going 0 plus 9E gives me 9E. Now I'm going to follow this up to the 6E battery up through the top branch. And notice as I step from red to purple, I'm stepping from 9E and then I go down 6E. So if I'm at 9E and I step down 6E, this purple here is 3E. So check it out. I have all three of my elevations labeled. So actually, that's super cool. I can find kind of whatever I want to find now about this circuit. So for instance, if I wanted to find the current through the 12R resistor, right? That's one of the things I'm asked for here. Well, I know that the potential over the 12R resistor is going to be equal to 3E because the 12R resistor goes from green to purple, which is 0 to 3E. So the current through the 12R resistor is just going to be the potential across the 12R resistor divided by its resistance, which is 12R. And again, the potential drop across that resistor I know is 3E. I just mapped that out, purple to green, over 12R. So that gives me E over 4R. I just found the current through the 12R resistor. Cool. Now let's do the 18R resistor. Same thing will be equal to the potential over that resistor divided by its resistance, which is 18R. The potential difference over the 18R resistor, that's red to green. So that the difference between 9E and 0 is just 9E. So that's going to be 9E over 18R. So that gives me E over 2R. There's the current through that branch. Then finally, we want the current through point A. So to do this, I don't have a resistor. I purposely did not put a resistor in that bottom branch. So we kind of got to think about what's going on here, and we need to consider what the currents are doing and then consider the junctions. So I'm going to change my color out here for this analysis. I'll use purple for currents. So I know the direction, I know that current always flows through a resistor from high potential to low potential. It's just going to, it flows downhill, right, with the electric field. So for instance, I know that through the 12R resistor, I know that I have current, my I12R flows down from from purple to green through that resistor. And for my 18R resistor, again, it flows from high to low. So I know that the current, that 18R current, flows from left to right through that branch. So think about it. If I have current entering this junction right there, and it's entering from left to right through the 18R resistor, and from the top down through the 12R resistor, conservation of current, that current's going to have to go this way, right? So I'll call this I sub A. So those two are flowing into I sub A. So that tells me that I sub A is just going to be the sum of those two. And that's just looking at junction rule. And you can think about, basically that's like sum of currents in equals sum of currents out. So conservation of current there. So when we sum those, we'll have 3E over 4R. Okay, so that was a way to find currents using potential analysis. Now I'm going to do this problem again, and we're going to use Kirchhoff to do it. I'm not a huge fan of Kirchhoff, and this problem illustrates why. I mean, sometimes you have to use this. Sometimes you have no choice but to use Kirchhoff for an entire circuit, or sometimes just a part of a circuit where you don't have enough information to be able to do the potential analysis you might want to do. And you can say use potential analysis for like 70% of your circuit, but then you've got like a little piece somewhere that you have to use Kirchhoff for. That can happen, and we'll probably see some examples of that. But for this problem, we were able to actually completely solve it using potential analysis. This is, again, the higher level approach to this type of circuit. But I do want to show you what Kirchhoff would look like. That's a good skill to have. So let's consider the circuit again, and now let's use Kirchhoff. Kirchhoff is less conceptual. You can kind of what I see is that students are able to apply Kirchhoff and not really think about the circuit at all, right? Like not really connect to it at all. It's a very superficial analytical method, but like I said, it's a useful tool. Sometimes you want it. So for Kirchhoff, you pick currents, just pick current directions, and it totally doesn't matter if you're right or not. It absolutely doesn't matter. So what I would pick here maybe is I might look at my batteries, and I might say, well, I think, if I look at this battery, that this current must be going this way. And I think this bottom, if I look at the battery, this bottom current must be going this way. So in order for the whole thing to flow, this middle current must be going to the right. And I'm going to name these. I'll call the bottom one I1. I'll call my middle one I3. And this top one I2. So I would have three currents and I would name them. Whenever I label currents, I always use straight line arrows to label currents. I see students quite a bit use, and I think this is just taught in other places maybe. I'll see students that use like a little circle for their currents. So they'll use something that looks like this for current, and that is just so misleading to use those little cycles, because what that can represent, or what that makes your brain think, is that there's some current that's flowing like around in a circle around this top loop or something. There's not a current loop. There are three branches with three different currents. So don't use, my advice would be to not use any kind of curly arrows. So I usually tell students, when you're marking currents in on branches, you really only need to mark the branch one time and mark it with a straight arrow, not a curved arrow. Okay. So we have these down. You can choose for Kirchhoff, choose whatever you want for your currents. Again, it doesn't matter. It doesn't matter if you're right or wrong. And then you just go around the loop and you do your summations and follow the rules. So we'll go ahead and do that. I like to keep track of it when I'm how I approached it. So when I go back and look at my work, I can make sense of it. So I will start, say, with the top loop, and I'll go around clockwise. Now, this clockwise isn't about the current direction, it's about the direction I'm traversing the loop as I apply Kirchhoff. All right. So that's what that's about. And I'll start at this upper right hand corner, say, and I'm going around clockwise. So the first thing I traverse is this 12R resistor. This 12R resistor has current I2 going through it. And as I traverse it, now again, this is in my traversal direction, right? Not the current direction, but my Kirchhoff traversal direction. I'm going through this resistor against the current. Yeah, so take that in and see that I'm going through this resistor against the current. The current is this I2, right, is going this way here through it. Sorry, I'm going to use purple for my currents. So if I were to draw in this branch here, that's just the direction that I chose for I2. And if I'm going to do my top loop clockwise, then I'm going against the current. All right. So if I go against the current, that means I'm going up the stairs, right? I'm not dropping. I'm actually moving upward from lower to higher potential. So that gives me positive 12R multiplied by the current going through there, which I'm calling I2. And then I continue traversing, following this, and then I'm going to kind of head this way through the loop, and I'm going backwards through I3. Notice that. So I'm going again against the current. So that means I'm stepping up through the 18R resistor multiplied by I3. That's the current through it. And if I continue with that loop here, I'm going to go now down this battery from positive to negative terminal, the battery there. So I'm actually stepping down 6E at that battery, and then I'm right back where I started here. So I say equals 0. So that is one of my equations that I get from traversing the top loop. Now I'm going to actually get rid of these little traversal arrows because I don't want them to get in the way of my next traversal. I normally wouldn't draw those. If you saw me in person, I'd be pointing to things instead of drawing those out, but I'm drawing them. So now let's do the bottom loop. And we'll do that clockwise as well. You can do what makes sense for you, but we'll do that clockwise. And again, I'm going to start from the upper right-hand corner, and I'll traverse this way around the loop. So I pass through the 9E battery, and I go from low to high in that battery. So I have a gain of 9E, and then I come around here and I go through the 18R resistor, and now I'm going with the current. So I'm going from high to low, right? If I go with the current, it's a drop. And again, it doesn't matter if you're right. So you might be like, wait, is that really high to low? Or, that it doesn't, for this method, it doesn't matter. You just have to be consistent and follow the rules. So, which is another reason I This is not my favorite method because you can go through it and be completely disconnected with what's going on. So this is minus 18R times I3, and then I'm right back to where I started. So that's really simple. There are only two components in that bottom loop, so two terms in there. And that's sometimes a check that I'll do for myself. This is a super simple circuit, but if I have a circuit that's a little bit more complex, I'll go through and I'll count how many components I have per loop and make sure I have the same number of terms, so I didn't forget anybody or I didn't like put anybody in there twice, whatever. So yeah, I have those two loops, and then I can just solve algebraically for currents using those loops there. In fact, if you just see this, look at this bottom equation, right? It's really super simple, and you see that you can solve for I3. Whoops, I3. That's a 3. Straight from that bottom equation there and get E over 2R, and you already have that current. And then once you have I3, you can pop that into your top equation and you can solve for I2. And if we solve for I2 here, what we'll get is negative E over 4R. So I wanted to do something like that and show you that, because we chose the wrong direction, obviously, for one of our currents, right? Um, so, because you saw how we did it last time, let me go back to the previous page and remind you that when we used this method, we actually figured out the real directions of current, because current is going to flow from low to high through your resistor. So what we figured out is in that top branch, we actually have current going like quote unquote backwards through that smaller battery. The 9E battery is pushing current the kind of quote unquote wrong direction through the 6E battery. That totally can happen. It happens here. It's not that there's anything wrong. It's not the same as the 6E battery switching polarity. That would be a different case altogether. In the water analogy, you can think about the 9E battery as being like a stronger water pump than the 6E battery. But the 6E battery is still like, pumping. It's still doing its thing. It's still on. It's just that the 9E battery is so strong that it's forcing the water the wrong way through the 6E. Um, and you might not have guessed that when you first saw this circuit and had to pick directions, right? You might just like be like, okay, both the batteries, obviously I have current that will be going in the traditional direction. So we were wrong about that. And all that happens when you're wrong about a current direction is you end up with a negative sign for your current. So if this happens, right, then all I don't change anything in your drawing, but you know that the actual direction is opposite from what you chose there. Then I would apply junction rule. Let's see, we have I2, we have I3. We just need to get I1 then here. I would apply junction rule. It doesn't matter. I can look at this junction over here. And if I apply junction rule to that junction, I have I1 going into that junction. I have I2 going into that junction. And I have I3 flowing out of that junction. So that tells me that I1 equals I3 minus I2. And again, I don't switch these back to like the actual directions if I know I'm wrong. You have to, with Kirchhoff, you have to stay with your original choices and just sub in, like be consistent throughout the entire solution here. It's just your interpretation of the solution that's different. So you would interpret that negative sign as meaning that you chose the wrong direction. Anyway, we have I3, I2, therefore we have I1. That's going to be equal to I3 minus I2. So that just gives us 3E over 4R. So we get all the same stuff that we got in the other problem, right? But we got it in kind of a different way. So this can kind of give you a feeling for Kirchhoff. So this I1, the direction was as shown on the diagram. I3's direction is shown on the diagram. It's this I2 that the direction is opposite. And I just want to remind you that when you're asked to determine currents in a problem, in a circuit problem, if I ask you to determine a current, that's magnitude as well as direction. So if you give me the magnitude, you also need to let me know the direction. If you're going to use Kirchhoff in a case like this, you could make a note, something like for your I2, you could say something like direction opposite to diagram. And that lets me know that you understand how to interpret the negative sign there on I2. But I hope really one of the takeaways for you from this problem is the superiority of this approach here, and that is considering potentials and using those to find out the architecture and behavior of your circuit.